My name is Rob Farrell, and I've been with NOARC for almost 2.5 years. And my role today is the Director of Research, Development, and Engineering for NOARC North America. That's a recently new role. Previously, I was the Director of Marketing for NOARC North America. And joining me today is Kunmi Odunoku. Kunmi is product manager for NOARC products in the US and Canada, and we'll be sharing the presentation duties today. So just a brief review of the agenda, introduction and overview. That's what we're doing right now. We'll be talking about high voltage and medium voltage transformers. We have some reference projects, some examples of high voltage transformer projects we've done in North America. And then Kunmi is going to spend some time talking about transmission and distribution components, both high voltage and medium voltage. And then, of course, at the end, we'll have time for questions and answers. So let me jump right in here. So a little overview of who NOARC is. NOARC is a subsidiary of the Chint Group, which is based in China. NOARC was founded in 2011, and the brand was created to provide specific focus in North America and Europe for the NOARC branded products. We have a headquarters for North America that's in Los Angeles, actually in the city of Pomona, a suburb of LA, and in Prague in the Czech Republic. The business is primarily low voltage up until recently, low voltage circuit protection, power distribution, industrial controls, and then more recently we've added pad mount transformers and the transmission and distribution products that we'll be talking about today. Chint, our parent corporation, was founded in 1984. It's truly a global company. We operate in 140 countries, something like 50,000 employees around the world. And recently had sales revenue around the world of over $22 billion US. So this is a very large, substantial, and well-established company that's doing business all over the world. The headquarters is in Shanghai, in China, and the Chint business covers low voltage components, assemblies, industrial controls and drive, automation and metering, all the transmission and distribution products we're talking about here today, as well as utility products, solar power, so that's modules and inverters, and battery storage. Basically, any electrical product that you can think of is manufactured in some way, shape, or form by Chint Global. And you'll see that the NOARC products are a little bit smaller in scope, but what I always tell people is this gives us the opportunity to take any of that core technology and bring it to the North American market. So that's really what our purpose here is within NOARC. Okay, so getting a little bit more focused on the NOARC organization. There's really 4 key things that we bring to the market in North America. Research and development. So my role is new as of October, and it's the result of a strategy by the corporation to create R&D centers in each of our 6 regional offices around the world. And the purpose of this is to ensure that we're taking into account the local code standards and customer requirements in the products that we develop. So my team is very much involved with the 1,200 or so low voltage engineers that work in our headquarters R&D center. World-class manufacturing. All of the Chint and Noarc factories are ISO 9001 certified, and the company has very deliberately invested in automation and production technology in order to ensure very high quality and to meet whatever manufacturing and delivery requirements there are. North American distribution. So under the Noarc organization, we have distribution centers in Pomona, California, Kitchener, Ontario, in Canada, and in Houston. And of course, having that those distribution warehouses in those locations gives us the ability to ship quickly into whatever area is required. And then, the last bit here is what I like everyone to take away is excellent products, exceptional value. That's really the value proposition that we deliver. The products are very good, both from a design and a production quality standpoint. We offer very competitive prices. Because of the scope and scale of our parent corporation, we can leverage volume to keep our prices low. To back all that up, we offer a 5-year limited warranty on most of our products. All right, so I'm going to move now into the power transformer manufacturing part of the Chint organization. We have two main power transformer manufacturing sites. In Shanghai, in the campus of factories there, plant number 108. It's about 40,000 square meters in size, pretty substantial size. 700 employees or more, and has been making transformers there for more than 20 years. And from that factory, we ship to 120 countries with these large power transformers. The other factory in China is in the city of Wuhan. It's a relatively new acquisition. It was formerly a GE factory that our company acquired a few years ago. It was opened in 2022, has similar capabilities to the main plant in Shanghai. But what I would say is it's more focused on specialty designs. And if you look at the table to the right, we can manufacture in those two factories anything from 132 kV all the way up to 1,000 kV. And in terms of annual capacity between the two factories, actually 3 factories, I'll get to that in a second, we have over 105,000 MVA of manufacturing capacity. So there's a lot of transformers that flow through those factories in any given year. As you can see, the Wuhan plant can handle transformers up to 1,200 MVA. So, for those of you who may not be able to picture that, if you don't haven't seen these transformers, that's an enormous transformer. The last plant I want to talk about here is plant number 110, also in Shanghai, and this is where we make our medium voltage transformers. We have less of an offering for North America from this factory, but it's got an annual capacity of 22,000 kVA, 22,000 MVA, between 10 and 35 kV in ratings. Okay, so talking now a little bit about the manufacturing capability of our factories. As I mentioned before, Chint has invested in manufacturing technology and automation in a very large way. And I'm not going to go through all of the pieces of equipment we've mentioned here, but the takeaway from this is that the manufacturing facilities are state of the art. I've had the privilege of being able to tour the main plant in Shanghai. And for a factory that's involved in a lot of heavy steel and process manufacturing, it is astoundingly clean. This factory is it just makes your mind spin at how well organized and clean it is. And really, so what that also supports is the quality of the product. You know, the auto welding, robotics, the CNC bending machine, the stacking platform. Those are all machines that are intended to improve the final quality of the product that we deliver. The last point on this slide is that we also have pretty substantial testing capability with a 2800 kV surge generator and a 7500 kilowatt generator that supports any of our short circuit and other testing. Okay, in terms of product certification and third-party testing, because we have been operating in so many places in the world, and because of the number of years we've been building transformers, we've had the opportunity to work with pretty much every major third-party certification and testing body that's out there. KEMA is probably the one that people here will recognize the most. And we've got a great relationship with those testing bodies and are constantly working with them on performing design testing for our products. KEMA is an especially good partner for us. And we've worked with them on some really major benchmarks in the industry. So our factory was the first in China to achieve a 750 kV rating. That's been third-party tested by KEMA. And similarly, the 132 and 220 kV natural ester insulating oil products have been third-party tested by KEMA. And so those are typically design tests. When it comes to meeting the local, regional certifications and codes and standards, we've worked with many different local organizations, including in North America, excuse me, ANSI. We've done testing to ANSI standards, UL and CSA. And you'll find that no matter where we go in the world, we'll find that we've done testing for the major markets. Sorry, I'm losing my voice a little bit here. So in terms of the product offering, and let me start with power transformers are usually very custom to the application, and so it's really difficult to get into the complete technical details of a large power transformer in the time that we have. And I'm not going to bore you by reading that list of transformer types, but you know, just take away from this slide that pretty much any transmission or distribution network transformer, we have the capability to manufacture and have experience in manufacturing those. Substation transformers and the large auto transformers, those are probably the highest, highest demand items that we manufacture. But there's lots of opportunity for specialty transformers for high altitude, high temperature, or even testing transformers. And then in terms of the scope of products, from 35 kV all the way up to 750 kV, we hit every major voltage class. And as I mentioned before, up to at least 1200 kVA. This is a highlight product that we would like to present today. This is a low loss transformer. And as utilities have been focusing more on energy efficiency, the specifications for this type of transformer have increased. So the concept of this transformer is that it has lower losses in the primary and secondary windings, which results in energy savings for the customer who's using it. Side benefit is it also generates higher short circuit withstand ratings, and low partial discharge, low noise. Those are the things that increase the lifespan of a transformer. So as you're looking for opportunities to work with our products, this is something that is very much a current product that we should be should remember and talk about. All right, so I'm going to go through now some reference projects. So these are projects that we've successfully completed in North America. So let me get started. So the first application story here is, excuse me, is for what the team in China called the Big Mac. This is a very large power transformer. It's a three-phase auto transformer. 525 kV is the primary voltage, and then 345 and 34.5 kV are the secondary voltages. The design is for a high short circuit withstand rating, and this transformer was supplied to a utility in the Western United States. I think there's some confidentiality around where it's located, so we can't really tell you exactly where. But this was a major project for us because of the size of this transformer. It's 525 MVA, along with being a 525 kV. That's getting pretty close to as big as they come in terms of utility transformers. It fully met the North American national standard, the IEEE ANSI standard. And because of its location in the Western US, it also had to meet some very stringent seismic requirements as well. Okay, so that's a great story for us. And if ever any of you would like more details, we certainly can work with you to provide something in writing that you can work with others on. Okay, so two more applications here. The 161 kV 15 MVAR reactor. So this was installed in 2013 in Canada. The end user is SECL. What's important about this also is that it's installed in the Hydro-Quebec system. And any of you who are familiar with North American utilities will know that Hydro-Quebec is one of the most demanding and highly technical utilities in North America. And oftentimes other utilities from both the US and Canada will come to Hydro-Quebec for references on projects they've done, because they know the amount of engineering clout that utility has. So this was a very good project for us. Not so much in terms of the product, which of course is quite suitable, but also to the fact that we met some very high engineering and quality requirements from the utility involved. Okay, and the last reference I'm going to talk about here is a 230 kV 200 MVA auto transformer that went to the Western Area Power Authority. WAPA is it's an organization that manages the transmission and distribution for about 15 states in the Western U.S., Central and Western U.S. It's a federal government department under the Department of Energy. This is a great project for us as well. Excuse me. The CHINT organization worked with a local sales agency to participate in the public bid. And when we won that bid, there were some very substantial challenges with the delivery and transportation. So one of the the milestones of this project was the fact that we used a dedicated shipping and logistics company and had this very large transformer delivered from Shanghai to the Western US in less than 2 months. We also provided on-site startup and commissioning, and the team there tells the story that when they were installing the bushings, a snowstorm was coming in, and they had to very quickly get the bushings installed to avoid having any moisture get inside the transformer. And then the final sort of crowning piece of this application is that once the transformer was commissioned, testing proved that the non-load and load losses were lower than the guaranteed values from the design. So what that means is that the losses and thus the efficiency of the transformer were much better than what we had originally designed the transformer for. So all in all, this was a very great example of high quality design and high quality manufacturing. Okay, so we'll pause for questions later. And so what I'd like to do now is move into the medium voltage realm. And talk a little bit about the recently introduced pad mount transformers that we're offering to the market in North America. And just to sort of bring everybody to the same level of understanding, pad mount transformers are integrated compartmentalized assemblies. They have separate high voltage and low voltage compartments, and those compartments then contain the high voltage and low voltage terminals. On the high voltage side, there's a load break switch, there's a tap changer, pressure relief valve, oil level gauge, and thermometer are all included inside the doors that you see on the front of the transformer in the image. These are a much more standard product than the high voltage transformers that I've been talking about. And they meet a very wide range of applications, from utilities to data centers, solar, wind, EV. These are the markets that this is perfect for us. They're designed for easy connectivity. They're designed for safety and reliability, and they're very compact, as is demanded in those applications I've talked about. In terms of ratings, our ZG series pad mount transformers are available up to 35 kV and up to 10 MVA in size. And you'll see on the table on the right, there's some of the available combinations are listed with primary voltages ranging from 600 volts to 35 kV. And then all of the corresponding secondary voltage is listed as well. And again, I won't read through all the list of features there, but the message for everyone is that this is a very comprehensive list of features, and there should not be any major competitors that have things that we can't match. Okay. So that's a quick overview of pad mount transformers. And so now I'm going to turn this over to Kunmi, who will be sharing with you the information on some of our high voltage and medium voltage T&D components. So I think I'm going to stop sharing now. So Kunmi, go ahead.
Thank you, Rob. Good afternoon once again, everyone. My name is Kumi Odunoku, and I'm product manager for NOARC here in North America. I'm just going to go through the T&D components that we have, which will be high voltage and medium voltage components. So, I mean, and for me to really, have you a good understanding of the product, I'd like to sort of give a little background to why we have those products. So the three products I'm going to be talking about is the high voltage insulators, surge arresters, and also the fuse cutouts. So I'm just going to give a little background to it, which kind of enhances our understanding of why we need for example, the high voltage insulators. If you look at the slide just right now, you see just a power architecture that shows, power from generation all the way to transmission and then distribution then to the final end user. So you see that, basically power is generated at, low voltage to medium voltage, and then it's transmitted at high voltage. And there's a reason why that is the case. What you see in the picture here is a generating station, and just immediately after that, you see a step-up power transformer, which transforms the voltage at that generating station to high voltage, ready for transmission on high voltage transmission lines. And there's a reason why that is the case. So one thing is that when you transmit power at high voltages, you create efficiency because you're reducing the losses on the line. From our elementary power equation, we know that losses is equals to the square of the current multiplied by the resistance. So the more, so the if you have a larger current flowing through the line, what that means is that you're gonna be having more losses on that line. So for example, and in most cases, you find out that the generating station is typically hundreds of kilometers away from like the place of application. So you want to reduce as much losses on that line, and that's why we typically transmit at high voltage. Now when what happens is that the transformer goes through a step-up transformer. What's a step-up transformer? A step-up transformer is just a transformer that transforms power from one circuit to another. So what it does is that it takes the power from a primary circuit to a secondary circuit. So the power is the same thing. It's always about the ratio of transformation, which is governed by the number of turns that are in those in both the primary winding and the secondary winding. In the picture above me here, you see that the primary winding has got lesser turns, versus the secondary winding. So what that means is that you're having a step-up transformer because the number of turns is directly directly proportional to the amount of induced voltage in the secondary. While for a step-down transformer, it's always the reverse. So you would have lesser number of turns in the secondary versus the primary. But the important thing I want you to understand is that from the power equation, since the power in both the primary and the secondary is the same, what happens is that there's an inverse relationship between the current and the voltage. So where you have the step-up transformer where the voltage is going up, the current is going to go down by the same transformation ratio. So if the voltage is going up 10 times, then the current is going to be reducing by the same transformation ratio. So what the transmission line effectively does is that it's reducing the amount of current. And when you reduce the amount of current, you know that the dimension or the cross-sectional area of the conductor would also reduce. And that's an important thing because, again, the transmission lines, they have physical structures that support them. If you have heavier cables on them, or like if you have cables that are, heavier, what it means is that it's going to cost the support, those structures might not be able to support those kind of heavy weight. So this is just a background to understand why we need insulators. So now in my next slide, I will just show you. So in a transmission line, for example, you would have insulators. And the reason why we have insulators is, I'm going to explain it this way. So in the second image you have here is an hypothetical situation where you don't have an insulator. So remember, this is high voltage transmission, and voltage is almost like is akin to, say, high pressure, right? It's like the pressure that drives water through a water pipe, for example. So the higher the voltage, the higher the pressure, basically the electrical pressure now. So if you are transmitting, for example, without an insulator, what is going to happen is that because the current is flowing through those lines, you have a situation because of the high pressure, some current will escape to surrounding areas, right? And they will create a conductive path through the air. And remember that there are, metal physical structure that supports all these transmission lines. So what it means is that the current, the electrons is going to be jumping, into those metal physical structure, which you don't want because that poses a safety situation. So that's why you need insulators, right? Because insulators ensure that you create enough kind of distance between the conductor and the non-conductive part of the structure. So the insulators basically are meant to to sort of distribute the electrical field evenly so that it doesn't create leakage current into those structures around the transmission line. So that's why we need insulators. If you look at the picture below here, which is the third image, is again like a situation, an hypothetical situation where you are having a shielded electrical line that's having an insulation, shielded insulation around those conductors. It's just going to make that the transmission line, the lines heavier, which the structure might not be able to support. So again, we don't use those shields, and because of those kind of extra situations that you might get into. So you need those insulators to create that creepage distance, which helps to distribute the electric field around and make sure that there is no leakage current jumping from that conductive material of the conductor to the physical structure. So we do have different types of applications for these insulators. We use them on power lines. We use them, if you've ever seen electric train rail lines, you see this insulators are used also. We also use them for transformers, both on the LV and the HV side, because at the point where those lines, those HV or heavy lines are dropping into the transformer, you can have leakages there. So you need an insulator that ensures that those the current does not, you don't create a short circuit situation around the the transformer internal component. So if you've ever seen the insulators before, there are key important parameters that you need to remember. The first thing is the creepage distance. That is the distance around the insulation disc that makes up the insulators. Again, the reason why we have a lot of this disc around the insulator, or the insulator is basically made up of this disc like shapes around, again, is to be able to distribute the electric field evenly. And then it also helps to self-clean, for example, when there is rainfall, and it also creates mechanical strength. So that's why we have those creepage, and it's an important parameters when you are trying to maybe design an insulator for a transmission line, for example. Another parameter to think about is the basic insulation level, which is like the maximum voltage at which the insulators are meant to operate at. So for us at NOARK Chint, we have a couple of products. One is having a basic insulation voltage 140 kV up to 250 kV. We have an array of products in that in that specification. Also, the creepage goes from 355 all the way to 560 millimeters. In terms of the ambient operating temperature, it's from -50 all the way to 50 degree Celsius. We do have the ANSI standard on this insulators, and we have a third-party test report, which is from KEMA. The other one is a higher level insulator with 780 kV bill, which is the maximum insulation voltage, and the creepage distance can go up to 560 millimeters as well. So this is the high voltage insulators that we offer. We also have another product, which is the surge arresters. Now, the surge arresters are basically devices that helps to clamp over voltage in an electrical system. So it could be over voltage spike as a result of maybe operational use, or it could even be from lightning as well. So the important thing to remember about voltage spike is that they are always very transient. And if you look at the image here, which is like one circle waveform of the voltage signal. Now, this image is just simply telling you that you have in North America the frequency of transmission is 60 Hz. So basically, what that is saying is that one cycle of this waveform, of this voltage waveform, takes it takes a time of 16.67 milliseconds to complete, to go from the positive alternation to the negative alternation. That's how much time it takes. Or in another way to put it, it's like 60 cycles in 1 second. So you're having this 60 waveforms in just 1 second. And what that means is that the opportunity for a voltage spike in 1 second can be 60 events, because you can actually have 60 cycles in 1 second. So you want to ensure that if there is over voltage in the system, that it is dealt with quickly. And the way to do that is to use a surge arrestor, which is a non-linear resistor, which is different from your traditional resistor. A traditional resistor is linear because it doesn't change, it's constant, right? But a non-linear resistor changes depending on the material that is used. So for example, the MOV, which is the metal oxide varistor, is voltage dependent. There are other types of nonlinear resistor that depends on temperature as well, but for this one it's voltage dependent, meaning that if there is an over voltage in the system that goes beyond the reference voltage, the surge arrestor, the MOV of the surge arrestor becomes like a parallel conductive path. So the resistance drop to almost negligible value. So it conducts that voltage spike away from the system to the ground. And that's why it's an important parameter. It's an important device. So a metal oxide varistor is a semiconductor device. So what happens is after the reference voltage is back to normal, then it becomes an insulator again for that transmission line. So we do have another parameter, which is the 2 millisecond square wave withstand current. That's the maximum current that the surge arrestor can withstand in 2 milliseconds, while the nominal discharge current is talking about the peak value of lightning current impulse that the surge arrestor is built to clamp or to attenuate. And so for us at NOARC, we do have surge arresters that fits into this categories, but let me just mention also that there are different sources of transient voltage spike. One is the lightning strike, which from studies we have approximately 900 lightning strike on the Earth's surface every second. So the transmission lines are constantly at risk of this lightning strike, and that's why it's important to have the surge arresters both for the substation and also on the transmission line. And the surge arrestor is basically installed in parallel to whether it's a station class equipment or the transmission line, because when it's not active, it's almost like it's acting as an insulator to the system. But when it attenuates or when it clamps or when it's about to start clamping, then it becomes like a conductive part. And since current will always want to flow through the least resistive part, then all that voltage spike will go to the earth through the surge arrestor. And we use them on the power substations, whether it's primary or secondary, and also on transmission lines. There are different types of them. The secondary type is the one you find in low voltage system, which are basically any power system that is on the distribution side less than 1,000 volts. So you find that in all your industries, even in residential area, in commercial buildings, and all that kind of environment. Then we have the distribution class, which is a medium voltage surge arrestor, and then the third one is the station class, which can go up to all the way up to 1,000 kV. It has the highest fault current withstand capability, and you can use it for both surges as a result of operation and also as a result of lightning strike. For us at NOARC, we have a solution for up to 120 kV. And in terms of the nominal discharge current, we have for 5, 10, and 5 and 10 kA. Again, these are all to the IEEE standards that is listed here below, and you can use them in altitude up to 2,000 meters. The third product that I want to talk about is the fuse cutout. So this you find mostly on the distribution side. So before the primary or the high voltage side of a distribution transformer, you will find the fuse cutout, and basically it performs the function of short circuit protection, opening and closing of the load current, and then also it's a means of isolation, because if there's ever a fault on a transformer, or if there is a maintenance work that needs to be done on a distribution transformer, it is through this fuse cutout that you are able to safely isolate the transmission line or the power distribution line, so that you can carry out any maintenance that needs to be done. So this is also an important component in medium voltage power distribution. And we do have two products. One is the porcelain type and also the polymer type. So, but both of them are rated 100 amps, while we can go up to 27 kV for the polymer type, and then the porcelain type, we would our rated voltage is only up to 15.5 kV. We do have the test report also available, the ASTER test report for this fuse cutout. One thing to note as well about this product is that it has good rated interrupting current capability, and it is so in terms of the hardware that goes along the fuse cutout, it's galvanized steel hardware and a NEMA bracket. So this is concludes all the components that we presently offer for the North American market for the medium and high voltage components.